chance. Yes, welcome everybody to my presentation today about induction melting technologies and processes. My name is Bernhard Nacke. I'm the head of the Institute of Electrotechnology at Leibniz University in Hanover. Our main teaching and research activities in the Institute are in the field of electrothermal and MHD technologies, so mainly in induction heating for melting, heating, heat treatment, and crystal growth. Today we want to concentrate on induction melting technologies, and a short overview about my presentation today. After a short introduction, we will talk more or less about conventional furnaces for melting, holding, and pouring of metals. That is the well-known induction crucible furnace. We will talk about the power supply and process control, then about the second type, the induction channel furnace, and something about efficiency and power consumption of induction furnaces. Then we will go to, let's say, more modern installations like the cold crucible technology, melting of metals in cold crucible, and the similar technology, skull melting and pouring for oxides and glasses. And then we come to some conclusions. So let's start with a general overview about an induction furnace installation. It is maybe not only for the induction crucible furnace, it is for general furnace installations. So in the main part, of course, is the furnace itself. Here it is a crucible furnace. It can be also a channel or a cold crucible furnace. Then we need a power supply because these furnaces are typically fed with frequencies above the line frequency. We need a capacitor bank to compensate the reactive power, which is very big of the crucible furnace, and of course then we need the connection to the mains. Those main aggregates we have to cool, so we need a cooling device for the furnace, mainly for the coil, and of course we need a cooling device for the power supply. This is normally split into two different cooling systems because they have different requirements. If we have a crucible furnace, we typically have a charging system, charging device, which is mostly combined with an exhaust device. And of course we have in modern furnaces, so modern installations, we have a so-called melt processor with using load cells to control the volume, the content of the furnace. I will go a little bit more in detail later. So, looking to the conventional furnaces, we have two different types. That is the induction crucible furnace and the induction channel furnace. The induction crucible furnace is, from the electrical point of view, an air transformer. That means we have here, the red is an induction coil that generates an electromagnetic field that goes mainly through the air, but also penetrates then the melt here, which is shown in yellow color. Due to the direct heating of the whole melt here, we have a very high density of power in the melt, which can be reached. But we also, you see here already, we have a strong steering of the melt. It is one of the big advantages of induction furnaces, especially induction crucible furnaces. And we have a so-called bath mirror that says an over height of the melt due to electromagnetic forces. So, due to the specific rules of induction heating, which was explained in the basics of induction melting by Egbert Barker in the presentation before, we have, of course, losses here in the coil. We have a certain efficiency. For example, if we want to melt gray iron, we have an efficiency of the system around 80%, and in total maybe of an induction melting system of 75% in total. So that means we have medium-high efficiencies, at least compared to the other type of furnace, induction channel furnace. And also to this general rules of induction heating, if we want to melt a melt which is more high conductive than gray iron, for example, copper, then the efficiency drops down. I will just explain this a little bit more in detail later, but first of all, I would say the efficiency goes down, so we have a medium high frequency, high efficiency with a an induction crucible furnace. Due to the effect that the steering inside the melt is dependent on the frequency, or let's say the ratio of steering to heating is dependent on frequency, so we can use higher frequencies to avoid a strong steering, but a stronger heating, and therefore we can increase the maximum power we can use for an induction crucible furnace. So typically this crucible furnace are used with higher frequencies than line frequency, typically maybe with, for example, gray iron with 200 Hertz. So on the other hand, on the other side, we have the induction channel furnace. The channel furnace is from electrical point a transformer type. That means we have a coil here which generates the electromagnetic field, which is now guided inside a magnetic yoke. Yeah? So that is the difference to the crucible furnace, where the main magnetic field is in the air. So here it is guided in the magnetic yoke. The secondary winding, so if we look to a transformer, is the melt inside a channel which is formed by a ceramic lining. This channel is closed by the bars here, short-circuited by the bars, and so we generate a secondary winding around the primary induction coil. Due to this transformer principle, we reach much higher efficiencies. So for example, for gray iron, we reach 96, 97%. For copper, instead of maybe 50 here, we reach with the channel furnace 80. For good systems, nearly 90% of efficiency. So that means the channel furnace really has a much higher efficiency compared to the crucible furnace, especially for materials to melt which has high electrical conductivity. But on the other hand, the channel furnace has a small disadvantage. Yeah? Directly we heat mainly only the melt inside the channel here, and this means the heat which is generated here has to be transported to the melt inside the bars. So that means that this principle is not called as a direct heating method like in the crucible furnace type. This is more, let's say, an indirect heating, and so the heat transfer to the bars is limiting the maximum power. So this is one disadvantage of the channel furnace, that the power is limited in order to avoid too much overheating in the channel. So the operating frequency is typically line frequency. There are no advantages using higher frequencies. We know that today some applications are working already with lower frequencies than line frequency. So going to the next. What are the typical applications of induction melting? If we are melting ferrous or non-ferrous metals, we can use the induction crucible furnace, as I have explained already. If we want to melt non-ferrous metals, we prefer typically the induction channel furnace. The only, let's say, negative point of a channel furnace is that the steering is less than compared to a crucible furnace. So if we need a strong steering inside the furnace, also for non-ferrous metals, we have again to use the crucible furnace, yeah, with a not so good efficiency. So if we talk about holding and pouring of metals, then we use typically an induction channel furnace, yeah, because we can realize a big bars, a big storage, yeah, with low power, which we need only. If we are talking about melting of high performance metals, we are coming to the cold crucible furnace, which I will explain a little bit later. And if we talk about the special applications, skull melting of oxides and glasses, we use also a kind of cold crucible furnace, but also a kind of inductor crucible furnace I also will explain later. So let's start with the classical crucible furnace. Let's talk a little bit about the typical design. Of course, first we need a strong steel frame which is holding everything. Then we have, of course, to handle high temperatures. So we put a special concrete first here in the bottom. On this bottom concrete, we put a special concrete ring, yeah, which then is supporting the coil. The red part here is a coil. And on top of this coil, again, we have a kind of concrete ring, which of course has also a spout on one side to be able to empty the furnace. So these concrete rings have the aim to support, to fix the coil mechanically, but also to insulate the high voltage of the coil. Typically we speak about 3, maximum 4,000 volts, yeah, against the steel construction. Yeah. So these concrete rings have a special aim, electrical insulation and also mechanical fixation. So then outside the coil we have these green parts here. These are magnetic yokes. Yeah? So these yokes are typically used to guide the magnetic field outside the coil to avoid too much stray field, yeah, for maybe people who are in this area here, and also to avoid heating of this steel construction here. Yeah? So, and then inside the coil we have the crucible, which is typically a part which is renewed after some time, after some number of charges or some time. Yeah, so for gray iron typically it's 2 weeks or 4 weeks maybe, then this will be completely renewed. So also we have here in the bottom in modern furnaces an open cone, or not an open cone, but a cone which is used to push out the crucible out of the furnace if it has to be renewed. Here you see a picture only of such a furnace. So here we have the frame, the steel frame, which I just have explained, with a spout here for emptying it. And then of course we need a second frame because we have to tilt this furnace to empty it over this spout here via this tilting axle here, and this is the second frame, and the tilting is typically done by hydraulic cylinders. This is a quite big furnace. It is a 12-ton furnace, high power, 9.3 megawatt. It's not a new one, but it's still the state of the art of this kind of furnaces. Here you see you have a view to the working area, the platform over the furnaces. I have to go back maybe. The typical working area is here on the platform of these furnaces. And so in the next picture you see this area here. Typically in modern installations we have 2 furnaces which are controlled by one control board. And so we have a pair of furnaces. Here you see only one. Here's just the cover of this furnace is open. This is the exhaust system here. And this man is here measuring the temperature of the furnace. So here this table shows an overview about the capacities, power ratings, and frequencies of induction crucible furnaces for different applications, different materials. The first part are the line frequency furnaces. They are belonging more to the past, of course. The maximum capacities for cast iron or steel that was built was roughly 100 tons, and the maximum power was 21 megawatts. The frequencies, of course, were line frequency, either for 50 or 60 hertz. For light metals and heavy metals, it was they were smaller. But looking to the modern furnaces, medium frequency furnaces, typically, as you see here, used in the area in the range of 150 to 1,000 hertz for cast iron and steel, or a little bit less for the other metals. For cast iron, or maybe I have to say better for steel, the newest development are 60-ton furnaces with a power rating really big of 42 megawatt. This is a trend in the steel industry that the classical use of arc furnaces are replaced by induction crucible furnaces. So this is, from my point of view, actually the biggest power for induction crucible furnaces. For light metals, you see again it is less here. Light metals mean, of course, mainly aluminium alloys. Heavy metals, copper or brass especially, I know what one big furnace installed in Italy, a 70-ton furnace with 16 megawatt. And taking into account that this furnace has an efficiency only about roughly 65%. That means 1/3 of this power is a cooling power for the coil. So looking a little bit more in detail inside the furnace. First I'm coming to the coil again. So here you see a typical drawing of the coil, and here you see the so-called active coil. What means active coil? That is a coil which is where the current is flowing, where the AC current is flowing, and which generates the electromagnetic field. So there's a limitation of the length of this coil, because if the length will be too long, the stray field will penetrate the steel construction here, maybe on top or the bottom area, and this leads to enormous losses and also maybe too much heating. Therefore, the length has to be limited. But in order to have also a good cooling of these parts on top and on bottom below the coil, typically a cooling coil is used. Yeah, here you see, which has only the aim to cool, so it has no electrical function. In the next slide, you will see here how it is realized. You see here is the active coil, one example, and here you see the cooling coil. In order, of course, also the cooling coil, of course, is penetrated by the electromagnetic field, and this generated some losses. And therefore, the distance, that is a kind of optimization, of course, the distance is optimized, yeah? So a little more gap between the windings to decrease the losses, but enough still to cool the lining behind. No? So this is a typical coil with active coil, and also on top and bottom the cooling coil. Here you see again, this is from a simulation. This also the coil here. Here's the melt in principle. Here you have the cooling coil, the upper and the lower cooling coil, and here you see additional two short circuit rings. Short circuit rings means it's a closed ring. The cooling coil is an open ring, of course. It's only for cooling, has no electrical aim, but the short circuit rings, they are closed rings, and short circuit rings are typically used also to avoid the stray field in this area, to press the active field away from the steel frames here or the bottom on the lower part. So now looking, it's the same figure, but now looking to the crucible lining, yeah, there are the typical requirements for the lining of a crucible furnace. One requirement is that it has the thickness should be as small as possible in order to realize a high electrical efficiency. So from an electrical point of view, we should decrease the thickness of the lining here, because maybe each, after my experience, each 10 millimeter less thickness, we have an increase of the efficiency of 1%. Yeah? So, but of course it's clear from other points of view, from the lifetime of the lining and others, we should not be too small. Yeah? We should avoid the metal penetration, and of course we should have a high mechanical and chemical metallurgical resistance. Yeah, so this is the thickness here, which is here 170.5, is still a compromise, yeah, between a good efficiency and a high lifetime of the lining. Yeah. So typically for melting gray iron, silica material masses are used for the lining of the crucible, which typically use boron oxide as a sintering add. And this material will be ramped inside the crucible between coil and form of the melt. And then due to this dry ramped mass, we finally get a structure inside the lining that looks like in this diagram. Here we have the side to the melt. Here we have the coil, the water-cooled coil. So this shows the temperature. So it's clear here just before the water-cooled coil we have a low temperature, maybe 100 degrees centigrade. On the coil itself we have a coil grounding to protect the coil. And then here we have the ramped dry mass, yeah, from here to here. You see this is 100 millimeter. And due to high temperatures here, from the melt, we got here first a sintered layer, which is very, very close. Then we got a so-called fritted layer, which is sintered, yeah, but not like here so hard. And then we got a loose layer. And this structure gives a lot of advantages. So for example, if we got, due to temperature changes, a crack here, and then melt is coming through the crack, then we have here somewhere on the back side, we have the loose material. So this liquid metal which goes through the crack goes through the whole volume and doesn't go directly to the coil. In any case, we have still this protecting layer here, the coil grounding, which is protecting the coil. So this is a kind of safety system for such crucible furnace. If we look to the energy supply of a crucible furnace, classically, of course, it's a line frequency supply. We need a step transformer to control the voltage. We need, of course, the compensation of the reactive power of the induction furnace. But due to the fixed frequency for line frequency, this compensation and also the balancing, this has to be adapted to the change of the impedance of the furnace. So this has, in principle, this capacitors have to be switched. In the case of converter feeding, converter supply, we typically use a converter which is the frequency controlled by the resonance circuit here of the furnace and the capacitors. So the frequency is changing and the capacitors are still the same, they are constant. So this is a big advantage also of the converter type, because we don't have to switch the capacitors, and also we don't need this balancing system to connect this to the three-phase system. Here's only a picture of a modern converter. It's a 16 megawatt converter, 250 hertz, applied for induction melting applications. And this is still using thyristors, yes. In these frequencies, thyristors have still advantages compared to IGBTs, for example. If we look to the resonance circuit, we have two possibilities. We can build a resonance circuit in parallel. So this is the inductance L is the inductance of the furnace, the induction furnace. This is the compensation, so we can circuit it in parallel or in series. Yeah? If we have it in parallel, we have to use a so-called I converter, that means current inverter. And if we use the series type, we have to use the U or the voltage type converter. But in principle, both are running and both have their pros and cons, but in total, more or less, they are the same. More and more a pair of furnaces are used, I have explained already. That means we are supplying two furnaces from one power supply, so we have to either to switch one furnace. So one furnace, maybe in this case, is now in the melting phase, while the other one is disconnected and is in the holding phase or treatment phase or emptying phase. Yeah? And then after melting this furnace, and again this starts to melt and this has to be emptied or to treat it. So this can be also done in modern systems electronically and not only a switching, so it's also possible to share the power from 0 till 100%, yeah, or 50-50 for example. So this is our very convenient systems today. This parallel operation has advantages that the customer has to pay only one time for the total power here. If he has, for example, two 10 megahertz furnaces, he has to pay only for a connection of 10 megawatt and not 2 times 10 megawatt. So finally, the melt processor system. This is also a point which is used in modern furnaces which have high power to control the temperature inside the melt, especially the overheating. So the principle is very simple. We put the furnace on load cells, so we always have an information about the content inside the crucible, and then the system is calculating the necessary energy for this volume which is inside the furnace. And if the supplied energy is reached, then it switches off the energy supply so that the melt cannot be overheated. And only if we again charge then new materials, and the load cell say, okay, the content is now increased again, I need more energy, I have to switch on again the energy supply, until finally I have a full furnace. I make a temperature measurement here, and I control the temperature, and then I start the superheating up to a certain temperature which I need for the pouring. So coming now to the channel furnace. I explained already the function of the channel furnace. Due to the fact that we have to transfer the heat from the channel to the melt, we have, of course, avoid overheating of the melt, especially in the channel. On the other hand, this kind of furnace doesn't have the strong steering like an induction crucible furnace. So in any case, we have to homogenize the entire melt. And in any case, we have to look for an efficient heat and mass exchange between the channel here and the furnace vessel, the melt in the furnace vessel. And that is the key point for the function, for the operation of such furnace. Okay, one is not, I don't want to go too much in detail, but of course the furnace vessel is one main part. If we think about 100 or 150 tons which are inside such a furnace, this has to be, of course, a strong steel frame design, but also the refractory inside the lining has to be realized in a good mode that we don't have problems with cracks. We have good insulation, thermal insulation, of course. Due to the fact that we don't have here the compromise between electromagnetic coupling and thickness, we can, of course, here increase the thickness of the lining as not as much as we want, but at least much bigger than in a crucible furnace. So if we look to the induction, in the inductor self, we call this mainly inductor, which is flanged under the furnace vessel. We have, on one hand, we have the one loop type. One loop means that we have a one loop of the channel. We have one coil here. You see it also in this cut here. And we, of course, we need one magnetic yoke. And this is the typical, for example, one design for a low power inductor, 250 kilowatt single loop for holding of gray iron, for example. Here you see a photo of such holding furnace, not the newest one, but you see here that we have a big vessel. We are emptying here. We put can take the melt here and transport it away. On the other hand, which is not visible here, you can at the same time refill this furnace due to the siphon principle. So for melting non-ferrous metals, let's say metals with high electrical conductivity, we typically use the double loop induction inductor or the double loop induction channel furnace, which, as you see here, has two loops of the channel. This is a typical inductor for aluminium melting. And of course, then we need also two coils, but we still need only one magnetic yoke. So of course, the magnetic yoke is one big part of such inductor, and that means that this double loop inductor has more or less with the same size like a single loop inductor, can fed with more or less double power ratings. That means for high powered inductors, the double loop inductor gives a lot of advantages. Here you see a photo of one plant, aluminium melting plant, 4 aluminium melting furnaces, which is then feeding a pouring system here. And here you have a look to the backside of the furnaces. Here is one inductor. Here on the bottom under the bottom is a second one. This is a quite low-powered system. Each inductor has only 500 kilowatt. So 2 inductors is 1,000 kilowatt per one furnace. I have some information that also these furnaces are supplied with inductors already with 1,500 kilowatt. I will show in my next table. Yeah, here is a development of a high-power inductor, specially developed for melting of copper and brass. It is a high-power inductor with 2,400 kilowatt. Of course, yeah, line frequency or at least a little bit higher, supplied by converter technology, quite heavy, 15 tons of course. And this inductor is specially developed for high efficiency. So this inductor reached for the melting of copper more than 90% efficiency, which is really very, very good. For brass it is roughly 88%. So here again a table of the capacities, power ratings and frequencies of induction channel furnaces. If we look to cast iron is mainly, as I explained already, used for holding, so power ratings are quite low. Aluminium, this is one installation I know, 6 megawatt, using 4 inductors, each 1.5 megawatt. And copper, I know one installation, 10 megawatt, using 4 of these high-powered inductors to 2,400, 500 kilowatt. For zinc, it is classical that they use several inductors. The furnace capacities are quite big, of course. Yeah, we have the chance here to use a big vessel for this channel type furnaces, and up to 160 tons. So maybe shortly, another use of channel furnace is a pouring furnace, which is an automated pouring furnace. So it looks like a typical channel furnace, but the vessel is pressurized, so we have gas here, which is then by pressure brings the melt level here up in the siphons, especially in the pouring siphon here. Here's a control system which controls the level, and so that the level here always is constant, and then the stopper always has the same conditions to fill the mold here. Also during filling, I can use the fill siphon again for refilling the furnace, and due to the control system by the level measuring device and the pressurizing here, we have still the same level here, even if we refill material here. Here, one picture of such a pouring furnace. It's a big one, 10 tons, quite big, 500 kilowatt power, and also for pouring furnaces, we can use a crucible inductor. Channel inductors sometimes have the problem that due to clogging, we got a closing of the channel inside. This can be avoided by a crucible. So if we have strong clogging, we can use a crucible for heating the vessel. But we have to take into account that this crucible, of course, has a lower efficiency again than the channel inductor. So looking a little bit to efficiencies or energy demands we need for melting. So here's a classical crucible furnace. For gray iron, we are in the range of 520 to 530 kilowatt. For other materials, you can see here. If we look to the next slide here, this is an energy flow diagram we see. So totally the efficiency for gray iron is roughly in the area of 75%, and the maximum losses, as you can see here, are the coil losses, the inductor losses, which are roughly 15% in this case. Additionally, we have converter losses, but they are quite small compared to the coil losses. So if we look now to this diagram, which you know already from the presentation of Egbert Backe before, you see that the final frequency, this is the inductor frequency, is dependent on the material we want to melt. So if we look to gray iron, and if we have a cold material, scrap, we have nearly 95%. But if it is melted, we have maybe 85%. But if we are looking to aluminium or copper, these efficiencies are much lower. This is, as I explained already, the disadvantage of a crucible furnace if you have to melt aluminium or a copper. So if we look to the energy flow diagram for melting of copper, we see so the big losses here in the coil, 36%. So in total we reach, after this flow diagram, roughly 53% efficiency only. So, and I will compare this afterwards with a channel furnace, and then we see what is the advantage of a channel furnace. But first of all, looking to the heat losses of induction crucible furnaces, depending on the furnace capacity, these heat losses are quite low. So if we look to maybe a typical 10-ton furnace, we see that this is less than 200 kilowatt. And a 10-ton furnace has maybe today a modern one, 8 megawatt, 10 megawatt. So that means we have only 2% of losses. So this is a very small thermal losses. We talk about a very high thermal efficiency, which is typical for induction melting furnaces, let's say. Also, we should take into account the stored heat, so that means when the crucible is still warm, hot at the weekend, and we switch off the furnace, so we should use the stored heat of the lining. That main users, main customers, they put already cold scrap to the lining and use the stored heat, so that Monday morning they have already preheated scrap then in their furnace. So if we look now to a channel furnace melting copper, we see that compared to the crucible furnace, we have a strong increase of the efficiency, 82% in total. The coil losses here are only 4%. I have next is the same for, again, for the crucible furnaces here. You remember it was 36%. So really, for melting of copper, we can increase the efficiency using an induction channel furnaces, but as I explained already, with a small disadvantage that the steering, of course, is much less than in a crucible furnace. So, therefore, then I want to leave, time is running, the conventional furnace and come shortly to the cold crucible technique. First, the technique for melting metals and alloys of metals. So if it is not possible to use a ceramic crucible for melting high-performance materials, or if the melt is so reactive that it will destroy the ceramic lining, we can use water-cooled, cooled crucible. Typically, the crucible is made of copper or copper alloys for good heat conductivity. Nevertheless, of course, this crucible has to be slitted, so that the material, that the electromagnetic field has a possibility to penetrate the metallic crucible and to reach the melt. So we have a slitted crucible. We have a strong steering, typically, of the melt inside. We have a strong meniscus of the melt inside. Also, the bottom is water-cooled, and this means that here we have contact with the bottom, so we generate a so-called skull, a solid layer between the melt and the water-cooled crucible here. And of course, we have to take into account that we have a lot of heat losses by radiation and especially by conduction here in the bottom area. So the efficiency, of course, of such cold crucible is not comparable with a classical crucible, induction crucible furnace. Here you have a view to the inside such a crucible furnace. In our institute, we have such installation here. Next slide will show it, and here you see the shape of the melt from top. So we have used this type of furnace for melting, for example, titanium, aluminium. It is possible to melt, to alloy, to overheat, and to cast with a cold crucible in one process. We have a good homogenization due to electromagnetic steering. The only problem is the overheating of the melt, because we still at the bottom we have the skull, we have solid material, we have the principle, the melting point of the material, and everything we have to, every overheating we have to realize inside the melt. So the overheating is still the key parameter to optimize this cold crucible. This is not running, sorry. So here you see you have a short view to the installation. Our institute is, we have a vacuum chamber because most of these applications, melting applications and pouring, we have to realize in inert atmosphere or in vacuum. So it is a vacuum chamber, and inside the chamber here you see a drawing. We have here the cold crucible. Again, here you see it with a coil, and then we have a rotating mold here, and then we can pour inside the vessel under vacuum or inert gas directly inside the mold. The cold crucible has a dimension of 4 to 7 kilograms, for example, of titanium aluminium. The power of our installation is 300 kilowatt and the frequency 10 megahertz. One application in the past was the pouring of such valves for automotive applications of titanium aluminium here to replace steel valves in order to reduce the weight, and therefore they increase the dynamic for the steering of this valves. So the last principle of induction melting is the induction skull melting technology. They also use the kind of cold crucible. This technology is mainly used for oxides and glasses. Oxides and glasses, they have the properties that their electrical conductivity at room temperature is very low, but is strongly increasing with temperature. So that means at room temperature we cannot inductively heat it, such material, so we need a special preheating. But if we realize these preheating methods for the starting, finally we will get at higher temperatures, we will get a coupling of the melt, so the electrical conductivity is increased against room temperature. We got a coupling, and then we can generate a melt inside here up to very high temperatures. We have realized already more than 3,000 degrees centigrade. That means we can really melt such oxides, for example, zirconium oxide. Due to the fact that this material is non-conductive at lower temperatures, we get a layer here between the water-cooled crucible, here in red, and the melt in blue, which is not directly heated by induction. And so we got a stable layer, and this layer we call the skull layer. And this skull layer that protects, of course, the melt against or from the crucible, and opposite also it protects the crucible from the melt, and the protection layer is of the same material like the melt itself. So this is a big advantage, so we can realize very pure materials inside the skull melting technology. Here you see the installation at our institute that we have started in 2001 with. It has 320 kilowatt. Skull melting has to use higher frequencies. Typically in smaller installations we have even tube generators. We are working in the megahertz area. Here in our sizes we try to use transistor technology, and we have used 80 to 300 kilohertz with good success. The works for starting were strongly supported by colleagues from St. Petersburg, Lady University, which are expert in this field of the technology. So here you have a view to the different types. This is a cold crucible technique. Yes, this is a cold crucible. Here is a coil. These are only water connections here because strongly we have to cool, of course, the crucible. This we have used mainly for oxides, like for zirconium oxide melts up to very high temperatures. But we also have investigated glass melting, and for glass melting we have used another type. We call it inductor crucible. That means here the crucible is a one-loop coil, which is the inductor itself. So we don't need two parts. We have only one part. The inductor itself is is the crucible itself, so we got a better efficiency compared to this type here. We have successfully used this for glass melting. The only problem is that, of course, at the connection part here, we have the full voltage of the inductor, and we have to avoid over-sparking here or the voltage problems here, but this can be done with special measures. This is unfortunately not running, but okay, at least you have a view to the surfaces here of such melt. This is aluminium oxide, zirconium oxide melt at higher temperatures, and this is already just before freezing. This is at lower temperatures. Here is these very typical structures at the surface. This is to the fact that these two materials have different densities and also different melting points, and they are freezing at different temperatures. So that was nearly all. I'm coming to my conclusions. I tried to show you that induction melting is an efficient and flexible method for melting of metals, which is classical, special alloys, and even for low conductive materials like oxides and glass, and has a wide range of applications. For conventional induction melting of metals, induction crucible and induction channel furnaces are used. Modern induction crucible furnaces are used at medium frequency, allow a very high melting rate, and an intensive steering. They only have lower energy efficiencies for high conductive metals like copper or aluminium. Therefore, crucible furnaces are typically used for melting of gray iron and steel. Channel induction furnaces have much higher energy efficiency, especially for high conductive metals, but limited power density and less steering. Therefore, channel furnaces are mainly used for holding and pouring of gray iron, and for melting of high conductive materials like copper, aluminium, or zinc. For melting of special alloys, which high required purity, crucible furnaces are used, but energy efficiency is lower compared to conventional induction furnaces. And finally, the skull melting in crucibles or inductor crucible allows melting of low conductive materials like oxides and glasses up to very high temperatures. So, dear colleagues, thank you very much for your attention.